So we're going to look at a couple of very powerful applications of things. So I want to start off with the Taylor series. Now, you should be able to derive a Taylor series for any function that has a clear recognizable pattern. And that would be things like e to the x and cosine x and sine x. You're not going to derive Taylor series for everything, just a handful. The main thing you're going to be doing is doing Taylor polynomials. That one, you don't have to find a pattern. If I say the fourth degree Taylor polynomial, that just means I'm going to take 4 derivatives. Okay, plug them in at the number in question. That makes life easy. So there's a few well-known power series. You don't have to know these. I would give these to you. But the most important one we said was the e to the x. Okay, probably the next one would be the cosine x. And I'll do the sine x as well. The sine x looks a lot like the cosine x, but it's shifted simply because the derivatives of the sine, shift from the derivatives of the cosine. They kind of alternate. So there should be a -1 to the n. And then this one's x to the 2n plus 1. So you notice this is all the even exponents. This would be all the odd exponents. Oh, okay. Now, if I know these, and we all have the ability to derive these, I actually did both of these last day. Then I want to discuss what I call the tweakages. So if I asked you to come up with the power series, let's say for, I want x cubed times the cosine of x squared. I want the power series for that. Because if I asked you to integrate this, that would be an absolutely gnarly, nasty, scary integral. I might be able to do it by parts. I might not. That one's really horrible. So what I would do, whatever the argument is, that's what goes here. And the reason you can do that is for these three particularly, the reason you can do that is all three of these converge for all real numbers. There are no restrictions. How do you know that? Well, if I just simply do the ratio test on this one, I'll find out in each case, because of those factorials in the denominator, when you do the ratio test, you're always going to get 0, which of course is less than 1 for all real numbers. So if I want to do this, this is going to be x cubed times, I'm going to replace the x with x squared. This is how you tweak a power series. This is one of the simplest things, yet most powerful things we can do. So I see an x, so that's now going to be an x squared to the 2n. Okay? With that, I can write the final answer as the next thing. So the coefficient part didn't change. Now, what's going to be the exponent? Anybody want to help me on that one? What's going to be my exponent?
4n plus 3.
4n plus 3, because first of all, the rule there is I multiply, but I can move this guy in and out because there's no n. N is the only thing changing. So x is almost treated like a constant or a coefficient in the sense that it's not affecting the sum. So I have 4n plus 3. And I'm done. That is the answer. Oh, cool. So if I needed to integrate this, I would just integrate this. That's actually one of the most powerful uses. So the Taylor series, these are very important Taylor series. I will not ask you in general to derive all these. I'll give you these and say, now tweak these. Now let's throw x's to powers. Let's throw other things in there. And there's some really powerful stuff. Now, one of the coolest examples of how you can use a Taylor series, believe it or not, is limits. Now, let's write down some of the most important limits that we learned in Calc 1. In Calc 1, we learned that the limit as x goes to 0 of sine x over x, we know that's 1. Hopefully you derived it in your calc class. We know this one is 0. And we know this one is 1. These are three of the most important limits. The basis of all trig derivatives come from here. So when I do my definition of the derivative, one of those always shows up. And the way I got the derivative of e to the x was to use this limit right here. Well, can I prove these not using geometry, not using L'Hopital's rule, can I prove these an alternate way? Yes, we can prove each of these using limits. Very, very cool. In other words, I'm sorry, I said using limits, using the Taylor series. So the Taylor series for the sine x, I just said a moment ago, I'll write it again. The Taylor series for sine x is the following. It's -1 to the n over 2n plus 1 factorial x to the 2n plus 1. So if I were to write out the first few terms of that, what would it look like? Because I kind of want an idea what I'm looking at, what I'm taking the limit of. Well, when n is 0, I'd have 1 over 1 factorial x to the first. Then I'd have, when n is 1, I'd have 1 over 3 factorial x to the third, then plus 1 over 5 factorial x to the fifth, 1 over 7 x to the seventh, and so on. Okay, that goes on. There's a dot, dot, dot there. It goes on forever. If I have then the sine x over x, then I want to take this quantity over x, which would be the equivalent of just reducing that exponent by 1. So this would now be 1 minus, and if you want to go ahead and evaluate that, that's fine. 1/6 x squared plus 1 over 120 x to the fourth, and then squeeze it there, minus 1 over 5,040 x to the sixth, and then plus dot, dot, dot. I want to take the limit now as x goes to 0 of sine x over x. Isn't that just going to mean I'm taking the limit as x goes to 0 of this?
And then you're just left with the first term.
Pretty much. Now, the reason I wrote it in this form, and I'm saying it's totally legal to do the plus dot, 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 because not only does this go on forever, aren't my exponents getting larger? I mean, isn't that kind of a no-brainer? And I'm taking the limit as x goes to 0, and the only thing left is 1. We did no calculus on this. We did not take a derivative. We did not do anything clever. We just said, let's take the power series. Okay, now let's take the power series over x. And now let's take the limit. And we got the 1. Now we know the answer is 1, but this one was probably easier to see than other things. Again, I didn't have to take a derivative. I have this infinite sum where all of these terms are going to be 0 when I take this particular limit. It's kind of crazy. Okay.
So would this only work if you're taking the limit to 0? What about
well, thing is that you can't, for trig functions, you can only take the limits to 0 because a limit to infinity wouldn't exist for the trig functions. But can I do this general concept with limits to infinity? If I set it up correctly, for example, just hypothetically, what if instead of saying sine x, I said the sine of 1 over x? Now I could take the limit as x goes to infinity. You know, there's tweakages we could do to the question. So I can do infinite limits if the argument is such. Does that help?
Yes.
Okay, by the way, that's a great question. Right now, I'm doing these 3 because we already know these and they're extremely powerful. Let's do this one now, because that's an easy one to do with the Taylor series. So let me write that up high. So e to the x, I know, is the sum from n equals 0 to infinity, 1 over n factorial x to the n. I know this. I don't have to prove this. We actually derived it already. And it's so powerful, but it's so cool and so simple to manipulate. So again, writing out the first few terms, this would be 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, forever and ever and ever, and my exponents are growing without bound. Now, what is e to the x minus 1? What would that be? Well, it'd be this minus 1. So would you agree it would be, and I'll go ahead and evaluate, 1/6 x cubed. Are we cool with that? Now, finally, what is e to the x minus 1 over x? 1 plus a half x plus a 6th x squared plus forever and ever and ever things with larger and larger exponents. So finally, when I take this limit, I'm taking the limit of that polynomial. And once again, kind of cool, huh? Now, I did e to the x minus 1. I mean, I could do e to, to 2x, e to the 3x. I could do e to the x squared. I can mess around with this all day long. But the fact is, if I simply replace my function with its power series, I may be able to really, really easily manipulate the algebra. So that's kind of cool. That's a really cool application of using the Taylor series to take a limit. It's not how you take limits in general, but it always works because there are limit questions you might be asked where you say, this is just difficult enough or just confusing enough. And I did L'Hopital's rule, but I just don't see where it's going. And this is pretty straightforward. All right, now we're going to move on to the next kind of series. And so I'm going to do a little bit of background first, a little bit of algebra that I want to introduce to you. Basically, it's some factorial manipulation that's really powerful, and it's not actually in the textbooks. I think this used to be in the textbooks like a million years ago, and they stopped putting it in there, but they'll ask questions where you need the following information. I'm going to show you. You can't answer it without the following information. Yet, if it's not there, I don't know where you'd get it. I want you to consider the following. I have 2 times 4 times 6, all the way up to 2n. So I'm asking you to take the product of the first n positive even integers. So let's just say n is 100. Okay, so I want you to go 2, 4, 6, 8 to 200 because I want the first 100 positive integers. Oh, okay, so I would like to do this product exactly up to 2n. So, if I said, all right, what's 2, 4, 6, 8, 10? What is that? Well, I'm going to get out my calculator and we'll calculate that. 2 times 4 times 6 times 8 times 10, that's 3,840. Great. Well, that was easy because I only had a few. What if n is really, really large? What if n is a million? I don't know. What if n is really large? This would be a really difficult thing to calculate. I think we'd agree because it would take so long. Okay, so I'm looking at that going, darn, only if it was a, factorial. Well, it's not a factorial. Well, not yet.
Yet.
I beat you.
Okay.
How about if I wrote like this? 2 times 1, 2 times 2, 2 times 3. Is that the same thing? Can I say that?
Yes.
Do you see a factorial in there?
2 times
2 times n
n
factorial.
factorial.
Close. 2 times n factorial?
2 times 2 n factorial.
2 factorial n factorial.
No. How many 2's do you have?
N.
So 2 to the n factorial. Ah. So if I said take the product of the first n positive even integers, the answer is 2 to the n factorial. Now, let's compare it to 2, 4, 6, 8, 10. I'm a big fan of always checking just to make sure it made sense. What is the n here?
5.
5. N is how many terms I have. So according to this should equal 2 to the 5th times 5 factorial, which is 32 times 120, which is 3,840, which is what we got the first time. Well, I knew it was going to work. It's not really cause for rejoicing. It's more like, whew, didn't mess it up. All right, we got a cool little formula. If I want to take the product of the first n positive even integers, I now have an absolute formula. I don't have to write it all out. It's so much easier. Great. And that question's really not going to come up very often. Not that one. Not the first n even integers. Anybody want to guess what's going to come up often?
Odd.
The odds, yeah. So I got 1, 3, 5, 7, all the way up to 2n. In this case, 2n minus 1, because when n is 1, I'm here. So in other words, I'm 1 less than. So if I asked you to do the first 100 positive odd integers, you'd go 1, 3, 5, 7, 9, and you'd be ending at 199. That's the 100th. because 1 was the first one. I can't factor though. I can't, darn. If only I had the even numbers. If only I had a 2 and a 4 and a 6 and an 8. And if only I had those guys. Can I just put them in? Is that legal? No, unless what?
You divide by
Divide
the
by them.
2n.
Oh, is this legal?
Yeah.
Can I now say that 1, 3, 5, 7, 9 up to 2n minus 1 and this are exactly the same thing? Yes, I can. Oh, and by the way, what's my numerator?
2n, 2 to the n, and factorial.
Not 2 to the n.
Oh, numerator. I thought you said denominator.
Numerator. My numerator is just 2n factorial. Factorial's got to go outside the parentheses. And now what's my denominator?
That's the 2n, 2 to the n, and factorial.
Oh, that is cool. What do you think? Now let's test it. I'll always test it. Let's just do, let's say 1, 3, 5, 7, 9. Let's just take that much. Again, I don't need to do 100 numbers. I'm either going to get an answer that works or an answer that doesn't. So let's multiply these. 15 times 7 times 9. That gives me 945. Now, n is 5. I only have 5 numbers. So let's look at this. So what does this say? What am I going to put into my calculator?
10 factorial.
10
over
factorial, 2 to the 5th, 5 factorial. I don't really need to calculate 10 factorial. I'm just going to use my calculator. So 10 factorial over 2 raised to the 5th and 5 factorial. And my calculator says, oh, what do you know? Same thing. Well, yeah, we kind of had to. This is the formula we're actually going to find that we use. The evens is nice, but it's actually the odds that are going to come up. And you notice the denominator was the evens. So we have what's called a closed form. There's no dot, dot, dot. I use dot, dot, dot to ask the question, but notice my answer doesn't have dot, dot, dots. It's one very specific value. That's called a closed form of an answer. Infinitely preferable to anything where I have dot, 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 because dot, 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 you understand what I'm saying, but try to program that into a computer. No, I need something in that form. Okay, so we're going to use this a little later. This is just a little bit of algebra review or algebra introduction, depending on whether you've seen it or not. I don't know if you would have seen this or not. It's kind of obscure, and it really only comes up in the next thing we're going to do. So I want to remind you of something we already know from way back. Excuse me. If I said a plus b to the 0, a plus b to the first, a plus b to the second, a plus b to the third, we'll just do the first few, a plus b to the fourth. Each of these can be expanded without the parentheses, of course. So that one is just 1. That one is just a plus b, and that one is just a squared plus 2ab plus b squared, a cubed plus 3a squared b plus 3ab squared plus b cubed. You notice every term in descending order is always represented. A to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab to the 4th plus b to 4ab to the 3rd plus b to the 4th. This goes on and on and on forever. This is called the binomial expansion. And most of us are very familiar with, if I just said, look at the pattern of the coefficients only. If I only am looking at the coefficients, I'm going to see a 1, a 1, 1, a 1, 2, 1, a 1, 3, 3, 1, a 1, 4, 6, 4, 1. Now we know this goes forever. What's the name for this guy? Anybody remember?
Pascal's triangle.
Pascal's triangle, which is awesome. I can tell you the coefficients of the binomial expansion for every positive integer exponent by just looking at this. Can anybody tell me what the next row is without actually physically multiplying it? Okay, I'll do that and that. Okay, that's my contribution.
1, 5, 10, 10, 5, 1.
Now, how do you get this guy? Do you guys remember the trick?
You just add the 2 above it.
Yeah, the 2 that are diagonal above it. Oh, Oh, so I want you guys to tell me the coefficients of a plus b to the 100th power. Doesn't that mean I got to have the 99th already before I could do this? Yeah, this is called a recursive definition. I can't do the 100th unless I know the first 99, and that's really not practical. I could do the 5th power because I had the 4th power already. But if I wanted to start with this, it would have been a lot of work. So our goal is really, how do I get these numbers without having to go through all this? And I really don't want to multiply that all the way out. That's the thing. I want to avoid that. So we introduce notation here. You would have seen this in baby algebra, supposed to have seen it in baby algebra and in pre-calculus, although you may have skipped it in your classes. Definitely in Calc 1, because it's how we derive the derivative of x to a power in general. It's called the binomial expansion. And each of these numbers is the result of something called a combination. So some of you may remember this. N choose R with this notation that is not a quotient. N choose R is n factorial, n minus r factorial, r factorial. This is called a combination of n things choosing R. I have n distinct objects. R is a number less than or equal to n. How many ways can I choose R distinct objects? So I want to form a 5-person basketball team from our class roster. So I just grabbed 5 names at one time. How many ways could I do that? Well, it'd be the number of people in the class, choose 5, and then I would just do this on my calculator. It's a fairly simple thing to do. This is called a combination. Okay, if I asked you, let's say you have 100 people in a room. How many ways could you choose exactly one person? Wouldn't it be 100 because you have 100 choices? If I said I have 100 people in a room, how many ways can I choose all 100? What do you think? How many ways could I choose all 100 if I have 100 people in a room?
1.
There's 1 because I'm choosing all 100. How many ways could I not pick anybody?
1.
1, because, and that's just don't pick anybody. Would you agree that if I said pick one person, it would be the equivalent of saying pick which 99 people I want to leave behind? Would that be the same thing?
Well, statistically,
No, not statistically. Yes. Mathematically. Yeah.
yeah, I mean,
Because n minus r and r add up to n. Oh, so I'm picking r and I'm also picking which ones I'm leaving behind in a sense, which means that this is equal to n choose n minus r. That's always true. You notice the symmetry of the table. Oh, so what is this? This is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. This is 4 choose 1, 2, 3, or 4 choose 0, 1, 2, 3, 4, and 5. Every number in the binomial expansion comes from this. That's very, very powerful. So there's actually a formula, believe it or not. There's a formula for a plus b raised to the k power. And the formula goes like this. It's n equals 0 to k, not infinity, not infinity, of k choose n, a to the n minus k, oops, sorry, b to the k. So when n is 0, I have my a to the n, b to the 0. When n is 1, I have my a to the n minus 1, b to the first. All the way down to where finally n equals k, then I'd have a to the 0, and then b to the n. And then the coefficients are exactly those guys. But you notice it has a 0 in it. That, by the way, this is called the binomial formula. That's, you hopefully saw this in intermediate algebra. Hopefully you saw it again in pre-calc. And if you didn't, it's okay. It's not going to kill you. But familiarity is always nice. There's one that always seems to stump us, though. If I said n choose 0, like I said, I got 100 people in the room. I don't want to pick any of you. How many ways can I do that? You said there's one way. But what does this look like as a factorial? Well, wouldn't that be n factorial over n minus 0 factorial, 0 factorial, which leads to an interesting problem. What is 0 factorial?
1.
1.
So just equals
1.
1.
And if you're not sure, 0 factorial, this I'm yelling at you, 0. equals 1. 0 factorial is calculated. Remember, factorials end at 1. They don't end at 0. If factorials ended at 0, then all factorials would equal 0. So a factorial, 7, 6, 5, 4, 3, 2, 1 ends at 1. 0 factorial is a special case. And 0 factorial has to equal 1 because we already know if I have 100 people in the room and I want to pick all 100, or I don't want to pick any, there's exactly one way to do that. But that's what the calculation would yield. So 0 factorial, when you see it come up, just remember it's always 1. Okay. Now, I've got this. I know this. This is absolute fact. I want to use this to help me come up with a series, a different kind of series, though. So going back to one of these statements, if I had to evaluate a combination, let's say I didn't have a calculator with a combination key. Maybe my calculator's got a factorial key, but it doesn't have a combination key. Now that could be a little bit on the tricky side. So how could I do that? Well, let's look. So if I say a plus b to the k power, I know that the first term is a to the k. Think about what we just did with the Pascal's triangle. Then you know the next one is k, a to the k minus 1, b to the first. Agreed? Because remember how that went? It went 1, then the number, and then it had a whole bunch of other numbers. The next one is k choose 2. A to the k minus 2, b to the second. I'll do one more. And then a to the k choose, plus k choose 3, a to the k minus 3, b to the third. This goes all the way until I get to the b to the k term. But if I wanted to write this without using the combination notation, which is kind of our goal right now, that's easy. That's just k. What's k choose 2? What would that actually be? Well, that'd be k factorial on top and what on the bottom?
K minus 2 factorial
K minus 2 factorial
times 2.
2 factorial. Can I reduce this? Can I reduce this? I think I can. We've done this before. Can I make the top k times k minus 1 times k minus 2 factorial? Can I do that?
Yep.
And the reason I would do that, remember, I'm saying think about this like you don't have a calculator. Oh, so after all of that, I would get just k minus 1 over 2 factorial. Cool. Can I do the same thing with this term? Because I want to see if I can figure out a pattern. I want to come up with a pattern that doesn't require me to use this notation, just write things in this form. And there's a reason, I'll explain in a moment. So this would be k factorial over k minus 3 factorial, 3 factorial. So just like we did a moment ago, if I run off the first few terms here, I'd have k minus 1, k minus 2, k minus 3 quantity factorial. Then this would be k minus 1, k minus 2 over 3 factorial. Now, I can keep doing this. I can keep doing this for a while. So if I went through and I replaced these guys with quotients, look at this one. Look at this one. Can anybody tell me what the next one is without doing any work whatsoever? Can you tell me this without doing any work? Just by looking at the form of the answer.
K minus 1 or k times k minus 1 times k minus 2 minus or times k minus 3 over 4 factorial.
Perfect. And that's what we would keep doing this forever and ever and ever. You go, okay, seems like the other way might be easier, but there's a catch here. Right now, when I'm using this notation, k has to be a positive integer. There's no way around it. I can't say I have k objects and that number not be a positive integer. So if I said, let's change it to this notation, then it turns out there's a couple of liberties I can take. And one of them is, if I wrote, forget this for a moment, look at that statement right there. Am I putting any restrictions on that k? That k I am, but what if I wrote that right there? That doesn't look like it has any restrictions. That looks like that k can be positive, negative, fractional. I mean, I'm just doing k and then times k minus 1 times k minus 2 and so on. Well, turns out if we use this form, we can do that. Now, I'm going to make a subtle change. I'm going to say, let's let A equal 1 and B equal X. That doesn't cause any problems. In the binomial expansion, your A and B can represent absolutely anything. Okay, so with that statement right there, then I can say without absolute certainty, 1 plus X to the K, again, using the binomial expansion that we just went over. Okay, what was the first term? It was A to the K. So in this case, it would be 1. The next term was plus K times A to the K minus 1, which would still be 1, times that term. And then the next term was plus K choose 2. And then B to the second power. And then the next term would be K choose 3. Okay, now, this is absolutely correct because all I did was expand the binomial. Okay, this is more practical, not more practical, more useful because I can do more things. Right now, in this expansion, have I put any restrictions on this K in this statement right here? Are there any restrictions on my K?
Can be 0.
Why not? If K were 0, wouldn't all these terms be 0?
Okay.
And then I'd have 1 plus X to the 0 equals 1. It works. Turns out, if I allow K to be, okay, if K is a positive integer.
Well, I was going to say, can it be negative?
Okay, hold the thought. Yes. If K is a positive integer, let's say this is 1 plus X to the 4th power. Well, we know then the highest degree term is going to be an X to the 4th. That's true. Oh, but the next one's going to be a K minus 1, K minus 2, K minus 3. And the one after that's going to be a K minus 4. And then eventually I'm going to get zeros, aren't I? Every term after that would be a 0. So if this is a positive integer, I get exactly the binomial expansion I did before. But if K is not a positive integer, guess what? I never get a 0 term, which means this is now infinite. If K is not a positive integer, then the sum actually goes forever. Let's do an example. Okay, let's take something we already know. I'm going to take something you absolutely know. You know this guy. Is this geometric? Is this geometric?
Yeah.
Yes, there's my R. Agreed? This is geometric. There's my R. We know from previous, this is simply going to be this. R to the nth power. Well, that's clearly alternating. So and we know this is true as long as the absolute value of X is less than 1. That's not in doubt. We know this. This is something we already know. This is something we've been doing already. I would like to use this formula. Well, how do I do that? How do I use this formula? Well, isn't this the same as 1 plus X to the negative first power? Everybody see that?
Yep.
Therefore, what is K?
-1.
K is -1. And all I got to do is put the K's in there. Whoa.
Forever.
But what we need to do is figure out what does the nth term look like. That's the key to all the problems whenever you're doing a power series of any form, is to figure out what the nth term looks like, because then that's what goes in the summation. So let's write this out. This is going to be 1 plus -1 times X plus -1 times, what would the next number be? -1 minus 1 would be -2 times X squared plus -1, -2, -3, 3x cubed. Now, I'm not done. I have to figure out what is the nth term going to look like. I don't think it's that hard to figure out. So if I said plus ... now I'm certainly going to have a -1, -2, ... and eventually negative n. Do you agree with that? See how the numbers all match right there? All over what? N
n factorial.
x to the n, and I'll put plus dot dot. So this would be a proper expansion. I wrote a few terms out because I want to see a pattern. Do you notice your numerators are going to be factorials also? But there's a pesky -1 in there, isn't there? Can I rewrite this guy here? I'm going to write this as -1 times 1 factorial. Can I write this as -1 squared times 2 factorial? Would that be okay? Then what's this one? -1 cubed times 3 factorial. Oh, so I'd rather write this. How about -1 to what power?
To the n.
To the nth power, n factorial over n factorial. Oh my goodness. That means my nth term is simply -1 to the nth, x to the n. Once I figure out what the nth term is, I can now say the answer is the power series from n equals 0 to infinity of this. Which, by the way, wasn't that the result we got just a moment ago when we looked at it as a geometric series? Yeah, that was exactly the result we got. So that should seem totally cool to you. All right, hold on, man. Let me make sure I'm doing. Okay, now we can tweak things all over the place, but let's do a couple more simple examples. All right, now let's do one. Let's use a different exponent this time. What if I want to do, I have 1 over 1 plus x to the, let's see, I've got some notes posted. I don't want to do the ones I've already got posted because I've already done them. Let's say 1 plus x to the, let's say to the 3rd power. Now, you can always do these as Taylor series. I can treat this as a Taylor series, do all my derivatives, evaluate all my derivatives, but that's a lot of work. I don't want to do any derivatives. I don't want to do nothing. I just want to use this binomial expansion. This is actually called the binomial formula, and this is called a binomial series. So the first thing I'm going to do is rewrite this as 1 plus x to the -3. Therefore, my k is -3. That's critical that I correctly identify the k. Because if I incorrectly identified k as +3, then all I'm doing is 1 plus x quantity cubed, which is just a simple 3rd degree polynomial. This should give me an infinite sum. So if I do the expansion, okay, it's going to be what? 1 plus, then the first term is going to be k times x plus, then the next term is going to be k times k minus 1 over 2 factorial times x squared plus k minus 1, k minus 2 over 3 factorial x cubed. Now, I got to do this for a while, but the question is, am I going to get factorials or am I not going to get factorials? It's really not obvious. Eventually, what's my nth term going to look like? Plus, all right, -3, -4, dot, dot, dot. It looks like this is going to be 2 more, isn't it? So it's going to be the negative, okay, so it's going to be the negative of n plus 2. So -n minus 2, if you will, over n factorial x to the n, dot, dot, dot. All right, I have correctly expanded this. That's not going to give me the answer, but my answer is going to come from this. So really what I need to do is see if I can recognize a pattern. Well, that one reduces to 3. This would be 12 over 2, that's 6. This would be 60 over 6, that's 10. 3, 6, 10. That's not really very helpful. But what if I think of it in terms of factorials instead? Okay, so first of all, do I have a -1 to a power again? -1 to the first power, -1 to the second, -1 to the third. Do I clearly have a -1 to the nth power here? Everybody?
Yeah.
Yes.
Okay, my denominator is clearly an n factorial. Now, I would love to say I now have 3, 4, 5, all the way up to n plus 2. I would love to say that's n plus 2 quantity factorial. I'd love
Can't you
to say-
just say that divide over 2 factorial?
Perfect. That's exactly what I want to do. Just finish it off. Ah, so can I do this? N plus 2 factorial. 2 factorial. By the way, if I just write a 2, it's the same thing. But I'll leave it like that because that's where it came from. Got it. Now, this is correct. Can I improve upon this, though?
Yeah,
Absolutely.
it's n plus 2 times n plus 1 times n factorial, and that can just go away.
Oh my gosh. By the way, if I can write an answer without factorials because things canceled, that would be considered a superior answer. You would, no one here would write, my final answer is 10 factorial divided by 9 factorial. We say that's just 10.
There's-
You know, so right now I can say that my answer is n equals 0 to infinity. I know I'm going to have a negative 1 to the n, but what else? I'm going to have this, this, this. So if you want, there's a whole lot of correct ways I could write it, but maybe this the easiest to read might be something like that. I
Are you
write
dropping
all
the x to the n?
did I lose the x? What happened to our x to the n? Oh, I'm sorry. I was just working on the coefficient right here. Yes, there's an x to the n in the answer. We were just manipulating the coefficient here. So then x to the n, however you choose to write this, you could write this as a quotient. You could put this all together. It doesn't make any difference. Now, remember when I said it was 3, 6, 10? That was kind of hard to see. Oh, but if I think of it this way, if n is 1, I have 3 times 2 over 2. There's my 3. If n is 2, I have 4 times 3 over 2. There was my 6. If n is a 3, I have 5 times 4 over 2. There's my 10. So I got all my numbers back again. But if I was looking at 3, 6, 10, I don't know that I would see this pattern here. Cool stuff, huh? So we have just figured out how to write this as a power series.
And the only reason we're doing that is so that we can integrate it.
Well, there are other things we can do, but if I can write it as a power series, integration is one of the key things I definitely can do. You said, but I can already integrate this easily enough. You're right. You can. Well, what if I tweak? Let me do the first tweakage. Let's do 1 over 1 minus. In fact, let's go 1 over 1 minus x squared. I'm doing 2 tweakages at once here. I no longer have a plus sign, and I have an x squared instead of an x. Can we deal with it? Oh, yes. First thing I'm going to do is write this as 1, my x squared raised to the negative 1. I still want it to be a plus, though. So plus what?
Plus 1. Right. Plus.
Negative.
Is that legal? Yep, that's how I get around the fact that this wasn't a plus, because that's the thing that's now going to go in the x position. Turns out this is real. What I'm doing right now is going to be real simple. Okay. So my k is negative 1. Okay. So this is going to be 1 plus k, normally be k times x. So let's make it simpler. K times thing. What's thing? Negative x squared. Plus k minus 1 over 2 factorial times thing squared. If I had had an x here, you'd be writing x's. I have an x to a power here, so I'm going to write that where I would have written the x's. Let's do one more, because I don't think we're going to need to do very many terms here to see a clear, identifiable pattern. So here's what I want. I want the nth. So negative 1, negative 2, dot, 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 dot. Clearly that's negative n. I'm going to have negative x squared raised to the n. And then I put plus dot, dot, dot to remind myself it doesn't stop there. This is the most important piece of the problem. If I can figure out a clear way of saying that, then I have a general pattern and I can write it as a closed form, meaning I can write my final answer as something times x to a something power. I don't know what the something is yet, and I don't know what the power is yet. Now, I got negative ones, I got factorials all over the place. We agree. You agree that this right here is negative 1 to the n and factorial. We've done that one before. Is everybody cool with that?
Yep.
But what's this? Isn't that negative 1 to the n x squared to the n?
Yep.
Oh, how interesting. If I take negative 1 to the n and I multiply by negative 1 to the n, I'll make it easier on you in case you forgot the rules. A to the n, b to the n, isn't that a, b to the n? Isn't that always true?
Yep.
So wouldn't this just be 1 to the n?
Which is 1.
Which is just 1. So this is no longer alternating, is it? Ah, now that's one of the tricky things, because when you're doing these problems, they either alternate or they don't, but you got to figure it out. Well, but I got negatives all over the place. Exactly. I have 2 here. I have 1, 2, 3, 4 here. I have 1, 2, 3, 4, 5, 6 here. I will
So they're
always have
always
a-
even.
In fact, I'll have exactly 2n. This is critical because that means I do not have an alternating series. So I got that, I got that, I got that, I got that. What's left?
Negative n.
Negative n?
It's just
Oh,
x
yeah,
to
I'm
the
sorry.
2n,
No.
So
What's
what's
the
left?
x squared to the n?
to the 2n.
Can I write it like that?
The 2n. Sure.
So this, what's this? And it didn't alternate, by the way. If that's a plus, it alternates. If that's a minus, it doesn't. That's cool. Now, these guys are fast, simple, easy. The patterns were pretty easy to recognize. Okay, no way around that. Now let's go for the evil ones. Okay. These really are not bad. There's no question I can ask you with a negative integer exponent that you won't be able to fly through. It's not the integer exponents that are the problem. It's the fractional exponents. But the only fractional exponent we will ever do are halves. The reason is there is no pattern with any other fraction. I can't have thirds, fourths, fifths. No pattern can be developed. But if I take a half, positive, negative, doesn't matter how many halves, and you're always subtracting 1, remember k minus 1, k minus 2. If I'm always subtracting 1 from halves, don't I still have halves? Remember how many halves you have? You have 3 halves, 5 halves, 7 halves, negative 3 halves, negative 5 halves. If I subtract 1, I still have halves. And I have a really simple pattern of halves that I can follow. So let's consider one that I haven't done yet. Hold on. Okay. I have 1 over, sorry, which one do I want to do? Make sure. Yeah, this is appropriately evil. I have 1 over 1 plus the square root of 1 plus x. Now I can do this as a Taylor series. That just means I take a series of derivatives and I evaluate them and so on. But that would be gnarly because the derivatives just get uglier and uglier, and I got all these fractional exponents and awful coefficients and ugh. So how about if I write this as 1 plus x to the negative 1/2 power?
K is negative 1/2.
So k is negative 1/2, which is going to make everything just a little bit uglier. Would you agree? Those k's that were on top now are going to be fractions. Yeah. But we can do it. We have the technology. So I have 1 plus k times x. Oops. And if it helps you, by the way, because the next one we put a 2 factorial, if it helps you, that technically is a 1 factorial. We just don't bother writing it because it's a 1 factorial. But a reason that might be a good idea, because what's the next one? The next one has a 2 factorial in the denominator. And I may forget that that's the next one because the factorial goes with that exponent. So the next one is k minus 1 over 2 factorial x to the second. Okay. That one looks already nasty. It'll get worse. So then I have negative 1/2 k minus 1, k minus 2. Now, I have to figure out what does the nth term look like? Well, okay, negative a half, negative 3 halves, you know, dot, 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 dot. Ah. Oh, wait a minute, won't it? It's going to be some number of halves. It's going to, okay, do we agree there's going to be negative some number of halves? That's going to be an n factorial. That's going to be an x to the n. Do we agree with that? What goes there? I put the negative in front.
2n factorial over.
No. What's the next fraction? This is a fraction. What's the numerator? I keep going. Look at
N
your
plus 2.
1,
Sorry.
3, 5.
And
2n minus 1.
2n minus 1.
Perfect, because it would be the nth odd integer. Does that make sense? We've seen this movie before, haven't we? Like an hour ago or something. 1, 3, 5, 7, 9. What's the nth one? 2n minus 1. When it was evens, it was 2n. I know that's a 2n minus 1 now, based on our prior knowledge. Now, great. So when n was 2, it's just 1 and 3. When n is 3, it's 1, 3, and 5. When n is 4, it's 1, 3, 5, 7. Okay, I got that. Okay, folks, roll up your sleeves. Now our work is cut out. I got to figure out what to do with that bad boy. Or do we have all the tools necessary? Do we have everything we need to actually answer this completely?
Should we convert the odd ones to evens?
Not yet. Okay, let's one thing at a time. First of all, the negatives. How many negatives do I have? I'm all right.
Negative 1 to the n.
So it's negative 1 to the n. Clearly, it's 1, 3, 5 up to 2n minus 1. There's no doubt about that. Don't every one of them have a denominator of 2?
So we can just do 2n minus 1.
So 2, 2, 2, how many times?
2n factorial.
To the n.
2 times 2 times 2 times 2.
Oh, yeah.
Now, this is my numerator. You guys see this? Negative a half, negative 3 halves, blah, 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 all the way up to this. That's negative 1 to the n, product of the odds over 2 to the n. Over that n factorial. Now, that guy's not a problem. In fact, I'm going to write it like this just so you guys don't get lost in the process. Can I write it like this now? I just put these together. So far, so good? Do we know what to do with that guy exactly? Yes.
Yep.
So let me do it like this. I'm going to do it like this. And I'll do this in black. What did we derive a little while ago? So I'm going to erase this because this is, I don't need this anymore. I need the space. What did we just show a little while ago? What does that equal? Isn't it 2n factorial over what?
2 to the n factorial.
These don't cancel, they combine. So negative 1 to the n, 2n factorial. That's my numerator. What's my denominator? Well, it's going to be 2 to the n factorial times 2 to the n factorial. So the n factorial is going to be squared. Now you have a choice. You have 2 to the n times 2 to the n. There's two ways I can write that are both correct. I can write this as 2 to what power?
2n.
To the 2n, or I can write it as 4 to the
Nth power.
Is there an advantage either way, you suppose?
Don't combine it so you can. So
Doesn't it just depend?
I have to multiply these, but I'm not going to leave them like that. So either that or that. Does it matter? First of all, it doesn't. Do you have a preference? Is one easier to conceptualize than the other? I don't know, because I already have a 2n in the factorial. I have an n. You know, I would write it like that. I would write it like that. It doesn't matter. Well, let's say I do the 4 to the n. Okay. They're both the same thing. So what we just figured out is a closed form for an, the coefficient of the x to the n term. What I just showed you is not in any calculus book that has been printed in the last 40 years. This doesn't exist anywhere. This question is asked in every calculus book that exists. This exact problem is asked, and not in one of them do they give you the final answer. It's no, every one of them, they leave the answer like this, plus dot, 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 plus dot, 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 and then If you're lucky, you get this. Most of the time, it's not even that. It's as if they forgot how to do this problem. I don't know. That bothers me that a question that you will be asked in every textbook, yet the author who wrote the textbook doesn't actually know how to answer the question. That's scary.
Ancient, long forgotten calculus.
Literally, it feels like that. Okay. Now, what is my final answer? My final answer is the sum -1 to the n. And by the way, because of the two different sets of factorials, you're not going to expand and cancel anything. No, when I had n plus 2 and n, I could expand and cancel, but this is 2n. And no, there's nothing that can cancel there. So you don't even bother with that. Just leave it like this. This is actually Purdy. And factorial squared x to the n. Let's not forget that. So the binomial expansion of this is this. Now, again, one of the main reasons to know this, of course, we talked about integration. But you say, but I can integrate this. That's easy. Absolutely, you can integrate that. I have no doubt that everybody in this room can easily integrate this. Let me put a random arbitrary exponent on that isn't even necessarily an integer. Let's say a is any real number, which means of the infinitely many a's I can put there, none of them will have antiderivatives. In other words, I just made the question of the infinitely many values I can put for a. Other than a equals 1 or 2, you won't be able to integrate that, period. It's an absolute impossible question. But what does it do to our answer?
It was just added.
That's it. That's all it did to our answer. That's why I love this kind of stuff. We just took something that would have been virtually impossible. That's easy to integrate and manipulate and so on. So that's the power of this stuff. Now, when we talk about the impossible questions and all the calculation stuff, that's the next thing. That's the posted lecture I did. That I took it from April 21st. Last semester. It was a lecture from last semester. And then that means that we don't have to miss anything. That means we don't have to give up our review for the final exam and all that kind of stuff. And I think the quiz associated with that has exactly 2 questions. They're not terribly long, but if you don't watch the video and fall through and look at the lecture notes, you may not be able to navigate through the problems. So I've also got posted lecture notes on the exact same stuff. There's a lot of stuff in there, a lot of information. I do appreciate a few of you found typos. A dropped exponent or just something goofy when you're reading going, wait a minute, this doesn't look right. And I appreciate it when you let me know. I've had to completely fire my staff, and I fired the staff that fired the staff, by the way. So I've sacked that group, and then that group got sacked again. So I'm sort of in between editors right now. So some of you have been editing for me all semester, and I appreciate it. So we'll keep that going. All right, I'm going to stop there.